I'm seeing the number of folks showing up and the number of folks actually engaging online. I'm thinking people may be surprised by their 5% participation grade, those who are opting out here. So if you know people, I do have a record of who logs in on the Teams meeting. And this is supposed to be an in-person class, so.
Are we supposed to be logging in on Teams in class too?
No, not in class. I'm sorry. No.
Did you
no.
take attendance?
No, I have not recently.
Oh,
Since about
okay.
the beginning. All I was noting is that there are people who are not here and not online. So I may need to do stuff. So we talked about. I want to quickly talk about decidability. We are leaping to chapter 7. So basically, hopping over 5 and 6 for right now. And as time permits, we'll take pieces of those that we can. But let's put it in 5 minutes. Recap something about decidability. Some big ideas. So what is a feature of a decider? I have a machine that is a decider. What do we know about it?
It's going to halt on any input.
Yeah, it will always halt, and it will give an answer, basically. It'll give us an accept or reject, or a yes or no. Okay, then we brought up an interesting problem. Oh, what was that? That's it. We brought up the issue of staying with our same notation that we've been using. Acceptance by a Turing machine is, I don't want to say equal. Implies. That's what we want. Okay. Acceptance by a Turing machine. Can somebody state what that problem represents?
Undecidability.
Yes. I mean, what is acceptance by a Turing machine? What would be the statement of the problem is?
I was gonna say it's like, is that a
You're given what? Given
a
String.
yeah, okay. So given a machine and a string, and you can the question acceptance by a Turing machine is if you give me a Turing machine and a string. The question I want to answer is. Will this Turing machine accept this string or reject this string. Right? That's the question of acceptance by a Turing machine. Sorry if I asked it weird. That's what I was trying to get to. In other words, but we know that a Turing machine in general can do one of three things, right? It can either accept, it can reject, or it could possibly loop indeterminately forever and ever. So if I could do this, it implies that I could tell whether a Turing machine would ever stop or not. And so we formulated that little argument, the proof by contradiction. Okay, so you should kind of have a little feel for that. That's on page, to understand what it's trying to do, at least. Not necessarily reproduce the whole thing, but you could potentially see some question about what it's trying to do here. But basically it says, if basically in order to do this, decide this, I would have to have one of these. But through the contradiction, we see, well, if I had one of those, then I could feed a machine its own description as the input. And remember, if we set that up so that it would give the opposite answer, basically it makes a contradiction there. That's page 207, where basically it gives the answer that it would accept if it did not accept, and it would give the answer that it did not accept when it really did accept. So it's a little bit maybe weird. I think it's unsettling. It's a little bit weird that you sort of devise this machine and you flip. If it says that it would accept, then it's going to give back the answer that it did not accept, and vice versa. Anyway, what that all, if you trace through that, what it comes down to is these are both undecidable. And that's the undecidable means I can't talk and write at the same time. So what it means is that you might, does it mean that any Turing machine that you try to test, if you give a Turing machine a string, that it'll never stop? Or that every Turing machine that you could ever conceive of, you could give it a string and you'd never be able to know whether it accepts or rejects or stops? That's where people, I think, start to, if you start thinking of it that way, it's like, wait a minute, this is just dumb, because I can think of a counterexample, right? But the problem is you can think of some counterexamples. We're talking about, in general, what we want is a solution such that I can feed it any Turing machine and any string and have it processed. And I gave the kind of, right, to try and go to the extreme of if you had a Turing machine that had one state and just had one character on the tape, and all it did was look at the character and then go to an accept state, right? And it doesn't even care what the character is, it just jumps to an accept state. Well, okay, if you make sort of the ridiculous argument to the simplest possible state, then could I ever make a machine that could test that one specific example and see whether it stops? Well, yeah. Right? It's like, can you write a Java program that could tell whether another Java program, a Java program that had one print line in it that said hello world, whether that ever stopped. The answer is, well, yeah, I think I can solve that, right? But the logic is that while you can think of a specific example, that you could contrive a particular example, right, where you could find out whether this stops because you designed it to stop, and you can write a program that will look at it and verify that yes, indeed, it does stop because it can't do anything but stop. But that's so to kind of get past that initial, like, does it logically make sense that I can't write a program that can tell whether another program could stop? So if you think of it, I guess I get on what my initial response when long ago when looking at that, there's kind of an instant, well, wait a minute, I'm a pretty good coder. I think I could write a program to do that, right? But the problem is that you cannot, in general, write something that will tell. And right, if you really think about it very far, the number, that sort of space where you could write a program that could tell whether another program stops or not, that's a pretty small thing, right? I mean, you could look for an obvious, while true, and there's no breaks inside the loop, that doesn't look like it will ever stop. But what if it calls another subroutine? It calls another function that purposely does a divide by zero and then stops it. Well, okay, so the halting problem is undecidable in the sense that not only can you not tell whether a Turing machine will stop on a given input, we can also, since a Turing machine is as powerful as our computers that we understand today, the mechanism of computing that we use in all existing computers, we can also not tell whether the halting problem in its most popular form, for practical for us as program people, is you can't write a program that can tell whether another program will ever stop or not. Wouldn't that be a nice thing? Now, people brought up that they worked in IDEs, development environment, where they might get a little warning that this looks like a infinite loop or something like that in your novice typing in, creating a while loop or something, and you don't put change the loop condition. You could identify something like that, but that doesn't look at the whole program, right? You're looking at one little structure out of a particular program, and you might be able to at least give an indication. It doesn't look like you're changing the something that would alter the loop condition, so this will never stop. So there's some stuff. What do we take away? There's some stuff that you can't do. Computability, the computation has its limits that you can't tell whether a program will ever stop in general. How do we? How does the industry respond to that? What is the So if that's true, what can you possibly do? If you can't tell whether a program will stop, what can you tell about a program?
Never stops.
Well, you can. I'm thinking lots of mission critical kinds of applications. If you have, maybe the code in the nuclear football that they carry around, or remember seeing a patient in the hospital and they had a little device next to the bed that was a medication, right? They had an IV and had a medication device that would automatically inject, inject medication, right, on a time basis directly into the IV. And so, since this was for someone I knew and cared about, the first question I thought was, I wonder who wrote the software for that? All right, so it's a little standalone device. It's got digital output and stuff, and it's got a little nurse can come in and dial up what the dosage is per hour or whatever, and whatever. In the building, we could ask somebody around here in the nursing school. But anyway, you dial in how many milliliters per hour or something. And so that would be kind of a mission critical project. Way back, I had an opportunity to at least a minor just brush up against somebody who had was working on pacemaker software for heart pacemakers, and that sounds kind of mission critical. Things like launching missiles, things like I actually worked with somebody who worked on the F-15 control systems back in the day, and yeah. So what do you do if you have mission critical software? What do you try to do with it? A fail-safe, right? You try to make sure that it doesn't do something bad if it fails, right? I mean, like, I would hope that the little medication infuser or whatever they call it, if power goes out, it maintains some memory of what it has been doing, or we have a couple of power flickers. It's not like, oh, restart, let's see, 5 milliliters per hour. I guess I'd better do that. Oops, power just went out. I'm back on. Better do 5 milliliters again. Hope that kind of fail is not in the software. So there are, I'm actually trying to get to just touch on, there is a body of computer science theory and work that tries to look at code and come up with proofs of correctness to try and determine that here's what we say it's going to do, and here's what it actually does. So but that's kind of on a so we can look at theoretical proofs of correctness. Let's say it comes up with so in the code structure, essentially loops will so that involves things like constructing graphs of the different states that the thing can be in, kind of looking at like a state machine, or verifying that there's, between this statement and this statement, there's no change to any of the control variables of the loop. But there's only so far that can go. As soon as you get to more than, I'm thinking, hundreds of lines, thousands of lines of code, there's no practical way. The time to do this is way longer than the time to code it. And you can come up with all the arguments you want, but what ultimately is going to determine, how do you try to, anybody currently working in industry? So what do you do? How do you tell whether the program is going to be correct or not?
That's it.
Test it. And so, yeah, so the alternative, they're logical arguments, but ultimately testing, and the latest and rapidly developing part of that, for decades, people have been employed in manually testing code and having written procedures, test procedures are part of the design process, really, right? So hopefully software engineering has talked about the fact that as you're coming up with requirements, right, somewhere along the way, what has to be true about a software requirement? It has to work in the software, and
But that's what it's supposed to.
you have to, yes, sounds like. Say again?
It has to be something you could actually do with the possible.
Yeah, and you have to be able to, the code has to do it, and you have to be able to verify that it does it, right? So one of the essentials of software requirements is that they have to be specific and unambiguous, and they also have to be verifiable, right? So you can say, oh, the code will send a message to Venus every 6 months or something. I don't know. I pull that out of the air. Well, you have to have something, right, in the, as with real life projects that have to end up working and coming in within budget and schedule, as the requirements are being developed, there's also very close on the heels is a test plan development of, we know the code has to do this. How are we going to know that it actually does it when we get to the other end? Once we implement it, how can we tell that it actually is doing what it needs? So I was heading toward the idea that testing has been manually done by people for decades, and there are new and this is not brand new, but the tools are proliferating to allow automated testing that lets you build around the environment, right? You've got your executable program, and you have a software framework that lets you put in a fake user that can, instead of a person, right, you had to kind of, software testing usually involves trying all the paths that you think need, that you can travel through the code. If you've written more than probably a 25-line program, you know that the obvious paths that you expect the program to go down are not the full set of all the possible paths that the program can take, right? Because as soon as you hit the run and nothing comes out when you expect it to be printing something, you realize, oops, there was a path that I didn't realize the program could even go down, right? So coming up with automated testing is currently what industry is doing is setting up. The nice thing about that is you can set it up and incremental development. The last position I had in a local DoD project was coming up with building, right? We had lots of developers changing code, developing code. They're supposed to be testing it before they put it in the repository. And finally, a couple of years ago, they're still in the process of developing a routine of, I think they had down to about weekly builds. But they were striving to get like a daily, able to, overnight run the test suite so that you could take all the code that's currently in the repository, compile, and then run it through the automated tester that would take it through all the paths, versus, right, having some poor soul typing in and following a test procedure that they had to do. They've done this 20 times and it failed, but now the code has been changed and fixed, and now hopefully the 21st time that they're typing in this whole sequence themselves, it'll work, versus the automated testing that can just run, pretends that it's typing in, or to the executable. It appears that entries are coming from the keyboard, and it looks just like a person were typing in. Which kind of brings us back to Turing's definition of artificial intelligence. Does it go both ways? You can't tell whether a person or a computer is typing it in. So the computer, the executable, will think that there's an intelligent being on the other end of the keyboard. Okay. So sometimes stuff won't stop. How do we deal with that in the real world? Well, trying to find, we can't necessarily, right? We intend that the program will halt. So if the program is correct, then it should stop. And so hopefully we can find some ways to prove that it works. We can do some static looking theoretically at what controls the loop, and there have been attempts. There's some software code. There are utilities, frameworks that attempt to look at source code, and one of the things that is pretty standard anymore is looking at the software complexity, looking at the metrics of how nested are your loops, or how long are your procedures, or what's another? Nested if-else statements, along with nested loops. Those kinds of things can come up with a complexity number for the software that gives you an idea of how maintainable it is, right, or how junky code is. And then static analysis plus testing and some automation of that testing, so you can just run the same test over and over again and let it run by itself, and it doesn't take a suffering human being to, no human beings were harmed during the testing of this software. So that you can run, way more tests and they can do it really fast. So rather than a person spending 8 horrible hours typing stuff in, you can let the computer run and run just a ballpark, some of the test things that got automated on the project I was on went from like an 6 to 8 hour test time for the individual having to go through, type in the stuff, wait for the response. We had that, that was like reduced to a matter of minutes, like 4 or 5 minutes, and could have variable inputs so that we could test the edge cases and try every possible thing, and even randomize so that you could try things that you hadn't even thought of. Get there. So now, that as kind of introduction, moving into chapter 7, which is, so we've kind of gone. Here's how I imagine going. We looked at simple machines. We looked at more and more complex machines. We got to Turing machines, and we hopefully convinced ourselves that they are a good model of the kind of computability, the kind of computation that we can do actually on any real-life computer that we have available to us today. And we have this halting problem. We have some limits of what you can do to verify or to tell whether the thing will even stop by itself or not. And that's kind of a problem if you really, really want your program to stop, right? If it's important that your program stops, or, right, it's not just that your mission critical program, you can tell whether it will ever stop, but telling whether it stops doing a particular thing is the same problem, right? If you want to tell that your medication infuser will stop injecting morphine into the person at a reasonable time before it becomes unfortunate, then you can't even do that. You can't even tell whether, in general, whether the program not only will stop, but whether it will stop doing a particular thing. So what do we do about that, right? I mean, that is a practical problem. So hopefully we're getting some sense that this isn't just like a weird theory thing that, oh yeah, back in automata class, they said something about a halting problem, and oh well, it didn't really affect anything. It's like, well, yeah, I think there are some practical considerations in what that implies. It means there are great limits to what you can do about telling whether your program does what you want it to do. So, we take practically, we can ever, there are papers and stuff you can prove certain things logically, but again, the general case, you tell whether it's going to do exactly what you want to do. And I pretty much have to test every possible path that you can try with every possible valid and invalid input. So there's some stuff we can do, some stuff we can't do. Now we want to look at Um, Occasional time complexity. So I'm kind of been asking. So that's what Ben talking about. Can you even compute this, right? The citability question, the halting problem that you can't solve. So the next so this is in a real sense, kind of touches on the algorithms class. Let's start with something that you're all somewhat familiar with is the concept of sorting a list of values, right? There's there are a variety of methods to do that. Bubble sort, the selection sort. And these are small enough in themselves that you could come up with a reasonably good analysis and proof of that they will terminate, that they will, if you give them the right inputs. It's just a smattering of things that we'll do. We'll put a list of values into an ascending or descending order. It turns out that some of these are faster than others. And we're talking, what this whole topic is going to be is about how fast can you compute stuff, and are there limitations? Anybody familiar with the bubble sort? It's kind of the simplest. Sorry, Emily. Isaac, seen this before. Maybe even awoken in the middle of the night, shouting.
Oh, no, not it. Oh. That's a non-optimal sort.
Bubble sort. Anyone know? We haven't really gone into our.
It looks at two numbers at a time.
Yeah, bubble sort compares two at a time. Each pair of numbers. So it starts with 1 and 2, and then switches them if that needs to, and then compares 2 to 3. Switches them if it needs to, compares 3 to 4. So it goes through. We'll talk after we define what our the notation is. We'll talk about how relatively fast these are. They do the same thing, but some of them are more efficient than others. Big O notation is going to give us an upper bound for number of operations needed. So it's going to be somewhat it's a good word. It's going to be a somewhat relative measure. It's purposely okay, so we're trying to come up with compare algorithms to each other. Not so we're purposely not running on a machine. Squeaky. Not quite as bad as a chalkboard. Okay, so we have to take some considerations here. We want to relate processing time TechRAM so now I'm actually into chapter 7 of our textbook. So, for example, just for algorithms co-students, we are not going into the depth and detail and even the same approach. So we're hitting on the main definition of our Big O notation. But we will not be looking, we'll touch a little bit on the sorts as an example of variations that we can come across, but what we're going to be moving very quickly into, we're not going to look at specific algorithms like the algorithms class does, but moving on to looking at really trying to hit on the concepts of tractable versus intractable problems, what the nature of those are. So again, notation is looking, giving us an upper bound as a function of n. All right, so we're using the number of elements that we have to process as our control input to the function, and we're figuring out, if I have this many elements to process, how many operations have to be done on those in order to get my result? And we're not very worried about when n is 1 or n is 2 or n is 5. But as n gets really big, so we're from a practical standpoint, we're purposely avoiding the mathematician's favorite, the limit as n goes to infinity. Mathematicians like infinity. Computer scientists don't. So just to cut down the PTSD. Talking about as n gets really big, and really big is kind of relative, right? It's when you want to characterize what the shape of the curve. Does it go up fast? Increase. Fast, slow, medium. So let's look at, suppose we have a painting myself into the whiteboard because I really wanted to. It's just now that we have this, we should be able to list these. A bubble sort is, let's begin. 2 nested for loops, basically related to n. And so, if you have, how do for loops nested inside of each other work? If you have for I equal 1 to n, and for j equals 1 to n, what do you get?
Well, you go through the whole list first, and then you go through the outer list second.
Yeah, I mean they're
Basically.
right. So the outer one controls how many times you do the inner one. So you have the multiplicative effect. So if I have for I equal 1 to j and for I equal 1 to n, and for j equal 1 to n inside of that, whatever's inside that inner loop is going to get executed n times n times. So like n squared. So bubble sort looks like that. And so an upper bound, like worst case, actually comes out a little bit less, but its big O is n squared. That means, so just to supplement that, if I double the size of n, if my processing time is n squared, right? For so if I have an n squared function, and I say, okay, my processing time is related to the square of n. What if I put in 2n as my processing, or as the number of elements? How much longer is it going to take to process 2n elements than to do n elements? So make a number. If it takes 5 minutes to process n elements, how long for, oh, make it even. Put some real numbers in there. If it takes 5 minutes to process 100 elements, how long will it take for 200 elements?
25 minutes.
Yeah. How come? It's going to be the square of, right, if we show the map here, we put n in here, so it is, wait a minute, that's not quite right. You're going the right direction, but if it takes 5 minutes, we don't square the 5. We want to, what we have to do, so, come on now. So n is 100. 100 squared what does it take for well, when I square everything in the box here, it comes out like doubled. So my multiplier on here was 2, and that comes out to be squared 4. So so squaring comes into it. It's not quite on the 5 minutes, right? So the squaring happens on the multiplier. So 100 elements squared is how many steps were required. That takes 5 minutes. And if I double, I put the 2 inside of that square, that 2 gets squared, give me 4. And so, you know, our intuition, or our, I think human beings are most acclimated, or most, I guess, acclimated implies that you see it all the time. There are lots of things that are just linear, right? They're proportional to each other. So if you're going 50 miles an hour for 1 hour, you go 50 miles. If you go 50 miles for 2 hours, it gets you 2 times the 50. Linear things are nice because it's like, oh, I have twice as much work to do, so it'll take me twice the time, right? So I can plan my life. Of course, the reality of work is kind of more like this. You double the amount of work, and it takes you 4 times as long. Right? You know, we think, wouldn't it be nice if it took 10 minutes, right? I mean, it would. so many things in life are nice, predictable, linear relationships. So you have twice as much to do, then take you twice as long. But in the world of computation, doing algorithms, we actually run a lot more into non-linear things. So this is in Word as well. How about merge sort, quick sort, and all of these are among the fastest. What was that?
Big O into the water.
Yeah. N log n is much better. If we look at, it turns out this is the best you can do for a general sorting algorithm. Actually, is n log n. So if you're considering graduate work, I would recommend you not do your research on trying to find a faster general sort than n log n, because it is provably best that you can come up with. And it is considerably better. We'll look at some of the numbers. Well, we could do n log n here. Let's do this for n log, and I'll throw in the 2. So instead of multiplying n by itself or multiplying n by its logarithm, I will do, we'll just, because it's easy, do log. Oh. Since I picked a good number, I can do either one. I'll do log 2. So what is log 2 of 100? In other words, what power of 2 gives you something close to 100? Beautiful. 128-ish. So we'll call it 7. N is 100. So put a dot on there so the mathematicians will come looking for me with pitchforks and torches.
Why not use a way being equal?
Hey, that's a bad way. I'll put a dot and an equal and a question mark. We'll cover them all. I'll be accused of mathematical heresy. We're going somewhere with this. So we have n of 100. So how long for, it takes 5 minutes to process 100 elements. We're saying 100 times log of 100 So for 200, so like 200 times what? Well, it's not log of 100, but log of 200, which is much bigger. Yeah, actually, even a little less than, right? So we'll call it 8. So how much bigger is that?
By one.
By 1 on the log, but what, what's the ratio, right? It's 700 compared to, oops, 800 over 700.
Actually, it would be 1600 when it's
Yes, so I have that. 2 up front there. 1600 over 700 is. What am I trying? Actually, I'm trying to do 5 times 1600 divided by 700. 16 over 7. 2-ish. Maybe I'll call it 9. So this would take like okay, round check me. So which is better? Right, this looks lots better than this. Just pulling out some numbers.
Wait, where did the 9 come from?
6 over 5 times 16 over 7. Oh, other way.
I got 11.
Yeah, I got 11. I was just seeing if you guys are. Yes, 16 over 7 is a little bigger than 2. Not a little less than 2. So this is still pretty good compared to n squared would give us 20. And log n gives us a proportionate increase just to 11. Doubles that, but you can make a compare these as n gets bigger. Notice that as n gets bigger, n squared goes up quite fast. But as n gets bigger, the log of n is going up pretty slowly, right? So this is considered way better than this. And so these are, suitable for very small number of elements, but you wouldn't want to bubble sort, 10,000 items would probably be pretty slow. All right, so we introduced kind of working in some motivation for beginning of chapter 7. We'll be touching, let's see. Don't be overly concerned on the theorems in chapter 7. I'm going to kind of aim at we're looking at section 7.1 and trying to get a practical understanding of these, the big O notation. We'll give that a little more formal treatment next time. And then section 7.2, you can start looking at. We'll be moving in sequential order for chapter 7 here. But yeah, again, the theorems and some of his proofs are a little deeper than I want to go in on this. All right, we'll see you next time.